Hi everyone, this is Jeff Geisinger, and welcome to the sixth tutorial in our DIVA for Rhino tutorial series. In today's tutorial, we will be going over lighting control analysis, and we will be setting up two different electric lighting control simulations, one with a single lighting zone, and another analysis with two zones, with a dimmed lighting control zone and a regular or manual lighting control zone. So just to remind everyone, I am using the reference office, which is a south-facing shoebox-style side-lit office in the Boston climate, and the Rhino file for the reference office can be downloaded along with this tutorial. And in the previous tutorial, we went over how to bring in our electric lighting luminaires, and you can reference that fifth tutorial to understand how to download IES files and how to bring them into Rhino and how to set your luminaires in place. And just to remind everyone, these luminaires are on the automatically generated layer called DIVA luminaires, and the sublayer that these fixtures are actually on is on a sublayer that I named when I brought in the fixtures called slotlight underscore 39 watts. And you can reference that previous tutorial just to go over the steps involved in setting that up. So I also want to remind everyone that we will be using nodes for this setup. We don't need to reset the location. We actually don't need to reset nodes when we are doing this. We just want to use the same nodes that we utilized during our previous climate-based metric analyses. And all of the node geometry and the analysis grid results are stored. The geometry for that is stored here in the DIVA analysis services layer. And you'll see that I already have the nodes layer turned on, and I'm going to use that. I'm going to reference that as I set up my lighting control groups. And you'll also see that the analysis grid, which has the false color results of our most recent daylight autonomy simulation, is in one of the sublayers under DIVA analysis services, but I'll keep it off for the purposes of this tutorial. Also, we were using shading before. You can see here shading lowered. I'm actually going to go ahead and turn that layer off, even though I'm going to have to run an annual daylight autonomy metric in order to calculate the electric lighting predicted energy use and generate schedules for lighting. I don't need the shading layer to be turned on. The calculation that I ran in the previous tutorial for the dynamic shading control groups already calculated the geometry of the shading already came into play for determining the daylight coefficients for the daylight autonomy, and so I'll still be able to generate those shading control group schedules when I run daylight autonomy, and I'll be able to just reuse those daylight coefficients just to quickly evaluate the different lighting control schedules and predicted electric lighting energy use that will be based on this annual metric. And I'll, as I go through the steps for running again the daylight autonomy metric, I'll explain a little bit further what I mean by those daylight coefficients and what I mean by kind of reusing those daylight coefficients. So the next step would then be, when we're ready to set our control groups, is to go ahead and go to lighting controls under materials. It's the last option in this pull down menu. And you'll see that by default, the electric lighting off tab will pop up, and this says that electric lighting prediction will be disabled. So by default, you don't have any electric lighting prediction or control groups. But we'll go ahead and click on detailed electric lighting controls, and you'll see the option for lighting control groups pops up. And before I describe this in a little more detail, I'll just point out that you can always click on the question tab, the little question button, which is this sort of help button that opens up the DIVA for Rhino, the user guide that has some detailed information about how the different simulations work and the different parameters work within DIVA for Rhino. And when we click on the one in the lighting controls tab, it brings up the lighting controls resources, and it goes into a little bit of explanation about how the dialog box works for this specific setup. And it also goes into some detailed information about what the different operational controls are, and I'll reference that in a second. So you'll see that we have the prompt to select nodes, similarly to the way that we were prompted to select nodes for our shading control group. In a way, the nodes for the lighting control group are similar, that they're serving as for specific types of operational controls. They're serving as either as kind of like photocell sensors for photosensor control dimming, or mimicking the kind of amount of light on a person's desk in terms of manual controls, and that will influence the likelihood for them to either turn the lights on when they arrive in the office or turn the lights off when they leave. So we'll go ahead and select nodes but I want to make sure that we actually select an operation first, because that will influence the way that we select our nodes. And if you go to operation, you'll see that there are a few different types. So let's look at manual on-off switch first. So the manual on-off switch operation control is basically, so it's running on an algorithm called light switch. And what that means is that it's mimicking the behavior of users within a space and their likelihood to turn on or off the lights. And in a nutshell, so it's basically there's a probability that a user will switch on the lights depending on the illuminance that the user finds in the space when they arrive in the space. And there's also a probability that they will switch off the lights. The user will switch off the lights when they leave the office at the end of their occupancy or at the end of their day. And so the former, the probability that they'll switch on the lights based on it depends on the illuminance value that the node that we select, or that the worst node that we select is experiencing. And this is based on a study from 2002. So if I go to here, there's actually a link on the DIVA for Rhino user guide. So you can click on this, and there's a link that this PDF, it contains the model that DIVA uses for this manual control. So it's really just about the likelihood for switching on the lights when a user arrives, and then also when a user leaves. And if you scroll all the way down to the end, this is a long document, but you'll see that there are a few figures at the end where the probabilities of whether or not a user will switch on the lights in their space in the morning are kind of explained here near the end of the document in some diagrams. Depending on the illuminance of their work plane when they arrive, there's the increased the lower the illuminance that they encounter, the higher the probability that they'll turn the lights on when they arrive. And then there's also kind of the switch off probability when leaving. So I'll go ahead and minimize that. So yeah, this is just for the manual on-off switch, and so we have to tell DIVA, we have to indicate where the users are located in the space, and to do that, we'll select nodes. And so you'll see that when we select nodes, the DIVA or the Rhino toolbar, the Rhino command line prompts us to please select lighting control group nodes. And for this specific type, we'll go ahead and select nodes that are based on where the users are sitting. So I could select a node that is on the work plane of in front of each of the computers in the space. And then when I selected those sensors that are in front of the work plane, in front of each person's desk, I go ahead and hit enter. And so you'll see that 6 nodes have been selected for shading group number 1. And now you'll see that the next prompt is to enter the lighting power in watts. Now this is is important to note that the lighting power for the fixtures that you have in your space are not automatically kind of sensed or interpreted by DIVA. We have imported this specific type of light fixture, and we have 3 of them in the space, but DIVA doesn't know how to actually take the individual wattage for each lamp and kind of create an overall lighting power for the space. That's up to the user. That's up to you to input. So one has to be very careful about getting the right amount of calculating their own lighting power for the space and inputting it here into this dialog box. So if you'll remember, we're using three 39-watt light fixtures, and so our lighting power for the space is 39 times 3, and so that is 117. So that's the lighting power for the space. And when we're done. So we could add another lighting group, but we're actually just going to use this one lighting group for now for this first pass. And when this is ready, we can click submit. Great, so now we've submitted this lighting control group for the space. It's a manual control group, and we've indicated an overall lighting power, and we've indicated where the users are going to be sitting. That's going to be controlling whether or not lights are turned off when they arrive or when lights are going to be turned off when they leave. I am ready to go ahead and click the metrics button to start simulating. So again, we want to, in order to generate the electric lighting control analysis, we'll go ahead and click daylight grid-based and then climate-based. Just like we did with the shading controls, we want to run a climate-based analysis in order to get an annual result for our control group, so in this case for our electric lighting analysis. And we can leave everything the same that we had before and click Run Simulation. And now importantly, we do get this prompt. It's asking us if we want to reuse our daylight coefficient or .dc files. Now, if we say yes, we want to use these daylight coefficient files, then that means we don't have to rerun the timely daylight coefficient calculation, and that will speed things up greatly in order to analyze the electric lighting. And because we haven't changed, there's no real changes to the number of nodes, there's no changes to the materials in the scene or the geometry, we actually can click yes. And I mentioned before the shading. So our most previous run of daylight autonomy actually had the shading on, and we ran our daylight autonomy with the shading control group activated. So the daylight coefficients already have the information, the resulting information that was calculated as a result of the shading control groups. So we actually don't need to run anything again. So we can go ahead and just say, yes, let's reuse those DC files, and you'll see that speeds things up. It speeds things up quite a bit. Great, and when the calculation is done, which was much faster than usual, we will go ahead and click Load Simulation Data. So when the simulation is complete, a DaySim simulation report pops up, similarly to the report that we got when we ran our daylight autonomy without shading and then also with shading groups. And now we also get this DaySim report with a little bit more information now that we have a lighting control group indicated in our file. And so all this information about the daylit area and other and glare and shading control groups is the same as what we had before. But if you scroll down a little bit, you see that under the DaySim report for the top part, the last line now we actually have a line item for electric lighting use. And so here it says the predicted annual electric lighting energy use is for lighting control group 1, 707.3 kilowatt hours. So it is actually generating based on the lighting control schedule that we get as a result of our control group and the installed lighting power, we get an estimated annual electric lighting energy. And so 707 kilowatt hours. So keep that in mind as we set up different types of lighting control. We'll see that we'll be able to reduce that number by having photosensor dimming, or by dividing up the space into different control groups and using dimming as a way to use less lighting energy, and therefore use less lights and therefore reduce the lighting energy for the space. So as we continue to scroll down, you'll see some of the simulation assumptions are the same as before. For example, the occupied hours, the 3,650 hour schedule with the bump in the middle of the year for daylight savings. But then if we keep scrolling, you'll see that below the occupancy schedule, we have our lighting control schedule. And you'll see here it says that the lighting control group 1, which is manual control, has an installed lighting power of 117 watts, and it is manually controlled with an on-off switch. And so here is the lighting control annual map. And you'll see that the white represents when the lights are on and black represents when the lights are off. So you'll see that there's a bit of on and off happening in the unoccupied hours, and that's depending on whether or not the lights were left on when occupants leave the space, or if the lights were turned off. And as I had mentioned, that there is a likelihood that the occupants switch off the lights when they leave, but there is also, as you can see, a high probability that they still will leave on the lights when they leave, and that continues on to the beginning of the day. Now you'll see that there's a little bit of staggering in the morning about whether or not when the lights are turned off in the space, a user arrives in the space during occupied hours and finds that the work plane illuminance is high enough that they can continue to work without turning the lights on. Then that explains why there's a little bit of staggering in this beginning hour, and you'll see that in certain instances it carries off all the way up into the middle of the day, where we have a little bit of gray area. And so this indicates the manual control schedule that we set up. And again, the sensors that we used for this analysis are, let's say I'll turn off the analysis grid. You see that we picked one sensor in front of each desk, and DIVA is using it's sending the illuminance value in the worst case scenario for these 6, and that is what is driving the switch on probability when a user arrives in the space. If we had fewer nodes, or if we had maybe a node that's just the one user that's closer to the window, perhaps the probability that they will turn on the lights, it will be a little bit lower when they arrive. But you kind of get a sense that this is the extent to this is more or less like the way that manual control works, where we have a lot of lighting energy still wasted during unoccupied hours. And if we scroll down a little bit more, you'll see that we have our shading control results that we got from our previous analysis for shading control and for glare. And you can refer to the 4th tutorial to hear the explanation for the shading control results. Now that we ran a lighting control group for one control zone, let's divide up the space into 2 different zones, where we can control one of the zones with photosensor dimming, and we can control another zone with manually controlled dimming. So I'll go ahead and go back to lighting controls. And for operation, you can, just as another note, like we can still use the manual operation, but we can tailor it a little bit to improve the lighting energy consumption, or reduce the lighting energy consumption for manual operation. For example, we can use the switch off with occupancy. So that means that at the end of the day, when occupants leave, an occupancy sensor knows that there are no occupants. It could be thought of maybe as a vacancy sensor, so it turns off the lights when the space is vacant. So that would eliminate all of that the lighting usage that we saw in the unoccupied hours at night. But then also for this manual control, we could also go to switch on or off with occupancy. So that would mean that the lights basically just turn on when the user enters the space and turns off when the user leaves the space. And the lighting consumption would look a lot like the occupancy schedule, or the lighting schedule would look a lot like the occupancy schedule. And for more information on this, again, you can go to the resource file, or you can kind of, after running this manual on-off switch, you can try very quickly just running these 2 different switch off with occupancy and switch on off with occupancy, without having to reload or to recalculate the daylight coefficient files, and quickly see the results in the DaySim report for these 2 different types. But so let's go ahead and add a lighting group. So now I clicked on add a lighting group, and you'll see that now we have 2 different groups. We have lighting group number 1 and lighting group number 2. So let's keep lighting group number 1 in the back of the space as a manually controlled group, and we can select nodes based on that once we have determined the second lighting control group, which will be a photosensor controlled dimming that is a little bit closer to the front of the space. So let's actually select those nodes first. So I'm going to click select nodes, and I am actually going to have a I'm going to select a sensor that is, or a node that is directly beneath the center of my first lighting control, my first luminaire. So this is going to simulate or mimic a photocell that is kind of built in with this fixture or right next to this fixture in a space that would be activated by the varying or a kind of target illuminance level. So you see that I selected here this one sensor that is directly below this luminaire, and I will say enter. And so you see one node has been selected for shading group number 2. This should actually, these should read lighting group, but that's okay. So one node has been selected for this lighting group. And again, we have to indicate a lighting power. So I'm going to be saying, so that this is where we also have to be careful. This lighting group, this second lighting group, has only one lighting fixture, and so therefore the lighting power is just the power for that one fixture. So that's going to be 39 watts. And I'll make a correction for the other lighting group in a second when I change that. And you'll see that there's also a lighting set point for this control group. So my lighting set point, this is basically saying at what target lux will there be enough light for this electric light to be turned off. And I'll go ahead and keep it at the default of 300 lux. And then there's two more options. You'll see that there's ballast loss factor and a standby power. So I'll go back to my luminaire data, and I have that here already open in my browser, and you can refer back to the to the 5th tutorial to go through the steps that I took to navigate to the lighting manufacturer that I chose and to find the product data. But I already have it open here in my browser, and it is the Slot Light 2 LED, and I picked a light fixture that is 2.4 meters wide, and it has 39 watts of power. And I'm going to scroll down in this data, and I'll see that here for standby power, the product data indicates that there is 1 watt of standby power. And so that helps me to input in DIVA the standby power dialog box. So I go ahead and put 1 for standby power. And now what's left is the ballast loss factor. Now, since we're using an LED fixture, this is running on a driver, and the ballast loss factor really isn't applicable for this fixture the way that I understand. And so we'll actually leave that factor as 0. If we were using a more traditional fluorescent light or complex fluorescent that runs on a ballast, then the ballast loss factor comes into play. And that would be, if I just open up the resources for lighting control, the ballast loss factor will be the percentage of peak energy used by a dimming system when fully dimmed down. And but since I'm using an LED, I'm going to go ahead and keep that as 0. And so I have this lighting group set, so that's good. Now I just need to make some modifications to my first lighting group. So first, let's change the lighting power. So we have initially had all three light fixtures on this lighting control group, and so we had 3 times 39 for the lighting power. But since we only have 2 now, we will reduce that lighting power to 2 times 39, or 78. So that will be the lighting power for these 2 fixtures. And we're still using manual on-off switch, so let's go ahead and select nodes now for that. We previously had 6 nodes for this lighting control group, and now we only want 4. We actually only want the ones for the users who are here in the back. So I'll go ahead and click on those 4 in front of those rear desks. You'll see here I selected 4 nodes that are corresponding to these 4 desks, or the 4 occupants that are in the rear of the space, and I'll click enter. And so let's see, manual on-off switch. Okay, as I had mentioned before, we can add occupancy sensors to that. Why don't we go ahead and for now and just leave it at the defaults without occupancy sensors, and then maybe we can make one further tweak after changing after this pass with 2 groups, and we can see how much further we can take the electric lighting consumption. So once those are input correctly, just check the numbers, and I will go ahead and click submit. And those are submitted, and now that we have those lighting control groups submitted, I can go ahead and run the simulation. I'll click on metrics again under climate based. Everything stays the same, and I will click run simulation. And this will just take a few seconds to run. I would go ahead and say yes, we still want to use the daylight coefficients. Okay, so once that simulation is complete, I click load simulation data. And another DaySim report will pop up. And if I scroll down, you'll see that the electric lighting use, this is what we're looking at right now, the electric lighting use has changed. Now we have two numbers. We have electric lighting for each group. So we have lighting group 1, which was still manual control, and that was 471 kilowatt hours. And the second lighting group is manual dimming, and that is coming in at 113.6 kilowatt hours. And if we go ahead and I'll open up the calculator and I will add that up, 471.5 plus 113.6, that adds up to 585.1, which is a reduction from, I think it was about, if I open up this other one, our previous analysis with just one control group manually controlled was 707.3, and our new lighting control that has two groups adds up to 585.1. And so you see that is a reduction of the annual electric lighting energy use because of the photosensor dimming. And we'll be able to see an annual map of that photosensor dimming, of how the sort of schedules work for those two groups. You'll see here, if I continue to scroll down here in our report. So you see that the first lighting control group, the system has an installed electric lighting power of 78 watts. That's what we input, and it is manually controlled with an on-off switch. And so this looks a lot like the manual control that we had before, except now it is corresponding to only the 4 nodes that we had selected for the back of the space. And if we continue to scroll down here, the second lighting control group, which is manual dimming, it says here the system has an installed electric lighting power of 39 watts, which makes sense. We had it selected just for that one light fixture, and we had input ourselves 39 watts. It is manually controlled with an on-off switch, and the dimming system has an ideally commissioned photosensor control with a ballast loss factor of 0%. The photosensor has a standby power of 1 watt, and so this is summarizing the input that we had put in for this lighting control group. And just to clear any confusion, it's still manually controlled, because in terms of whether or not the lights are left on at the end of the day or whether or not the lights are turned off in the morning, it's still it's still controlled by the light switch algorithm. But during the course of the day, whether or not the sensor that we selected is receiving the target illuminance of 300 watts, you'll see that the lights are automatically turned off as a result of the photosensor dimming. But we still have a lot of wasted energy because of the occupancy, the manual controls and lights that are still turned on at night and in the morning. Good. So nothing here has changed because of the shading control. It remains the same. So we have now reduced our electric lighting energy, and we've done that by splitting up the space into 2 different zones, and we have a lighting schedule for those 2 zones. Now let's try to reduce the lighting energy consumption even further by using some occupancy sensors to reduce some of this unwanted electrical lighting consumption during the unoccupied hours. So to do that, we'll go back again to the lighting controls, and let's go make a change for both lighting control groups. So for the first group, I'll change it from manual on-off switch to manual off, to switch off with occupancy. And so that basically means it's a vacancy sensor. So the light will turn off when the space is unoccupied. And I could leave everything the same. Here we have lighting set point and ballast loss factor and standby power. Actually, so the ballast loss factor, I'm going to go ahead and also switch to 0. So I think this is associated with the fact that there is now an occupancy sensor, but it's going to be tied to our LED lights, so we can have that as 0, and we can have the standby power at 1, and we can leave the lighting set point the same. I believe that even if we're using manual occupancy, I believe that this won't go into play for this specific manual, since we're not using photosensor dimming. This is just a dialog box that's there for photosensor dimming. Now if we go to our second control group, I will also change the photosensor controlled dimming, change this operation from photosensor controlled dimming to dimming with occupancy off sensor. So again, using the occupancy off sensor, or thinking of it as a kind of vacancy sensor. So whenever the space is unoccupied, the lights will turn off, but it will still use the photosensor dimming that is controlled by our target illuminance and by the location of the sensor node that we have. So I can go ahead and leave everything else the same here. So once all of that is input correctly, I will go ahead and click submit, and I can run another metric. So again, clicking metrics, and then on the daylight, grid-based, climate-based, everything else stays the same. I will click run simulation. And I will say, yes, we can reuse that daylight coefficient file again. And I'll load simulation data once that's completed. Okay, now we get a third DaySim simulation report. And again, the important information that we need to hone in on is here the electric lighting use. And now we have 2 groups again, but you see that the results are dramatically different. So the predicted annual electric lighting use for lighting group 1 is 274.3 kilowatt hours. And you see the group is referred to as occupancy always on. So this description is a little bit misleading. I mean, occupancy, so we have a switch off with occupancy, so that basically means that if there is occupancy, the lights will be on, but the moment that there is no occupancy, the moment that an occupant leaves, that means that the occupancy sensor will switch off the lights, and that did dramatically reduce the amount of lighting consumption for that one group. If I go to my previous report for the 2 lighting control groups with just manual controls and no occupancy sensor, you'll see that it's a big drop from 471 to 274. And an even bigger drop here is with the lighting control group 2, which is photosensor dimming, but with occupancy switch off. So again, a kind of a vacancy sensor. The lights will be turning off when the occupancy is not there. And that has been reduced to 29.9 kilowatt hours. And that, if I go back to the previous report, is a huge reduction from, in terms of percentage, from 113.6. And so I believe that this previous group had 585. And now if I add up these 2 numbers for my current run with the occupancy switch off selected for my 2 groups, for my manual control and for my photosensor dimming, I'll go and clear everything, and I'll add up 274.3 plus 29.9. And so now I've reduced my annual electric lighting energy consumption to 304.2 kilowatt hours. So that's a big reduction. And now if I keep scrolling down, we'll get schedules, or we'll get our annual maps for those 2 types of lighting, for those 2 lighting control groups. And so you'll see here that the 2 groups are, they're looking good in terms of no lighting being turned on during unoccupied hours. So all of the white in the unoccupied zones of this schedule are turned off. So you'll see here there's a description also for the lighting groups. This system has an installed electric lighting power of 78.0 watts. It is manually controlled with an on-off switch combined with a switch-off occupancy sensor with a delay time of 5 minutes. And here has a nice explanation. The role of the occupancy sensor is to switch the lighting off, not on, when the lighting is activated. And the sensor has a standby power of 1 watt. And you'll see, so we have the the light switch controlled or the light switch algorithm controlled probability of the lights being turned on when a user arrives, and then when a user leaves, the occupancy sensor kicks in and it turns off, and that off position stays off until the user's arrive again in the morning. And for the control group that we have in the front of the zone with occupancy with an occupancy sensor and photo sensor dimming, you'll see again it summarizes the lighting power, and it says it's a manually controlled group with an on-off switch combined with a switch off occupancy sensor with a delay time of 5 minutes. And the occupancy sensor only switches the lighting off, again, not on. And there's a dimming system that has an ideally commissioned photocell control with a ballast loss factor of 0, and the lighting system has a standby power of 1. And so you'll see here that there, again, is because of the occupancy sensor that is turning off when there's no occupancy, there is no lighting use during these unoccupied hours, and then that carries out through the morning. And then during the day, when there's some daylight, whenever the sensor below that luminaire that we selected is receiving the target illuminance of 300 lux, those lights are turning off, which happens quite a bit during the day. And that combined with the occupancy sensor is what's resulting in a very low electric lighting energy consumption for this control group. Great, and so that wraps up the two different types of the two ways for doing lighting control with two different zones, and I've covered a few different methods within those two control groups for using occupancy sensors and photo sensor control dimming to reduce the electric lighting consumption for our reference office. And just as a reminder, if we go to the location where we have our file saved, so again, this is under my desktop. My file is called Reference Office T1. I can double click on the automatically generated local project folder that DIVA creates, and I go to grid-based, the subfolder. This is where DIVA is storing all of the results that we did today. So you'll see that there we have our effective DGP. We still have information about the shading controls because we still have shading control groups activated in our file. So that that effective DGP. So this is our new glare map, but the lighting is also generated, and you'll see that if I double click on some of these PNGs, this is the most recent lighting schedule that our DASIM report was referencing for the lighting group 1, for the group that has the manual control. And so all of those files are stored here in the grid-based subfolder. Great, and so yeah, again, that wraps up this tutorial. In our next tutorial, we will be looking at linking our model to an integrated thermal analysis. So we'll be running a thermal analysis for our reference office, and so integrating these lighting results as well as the dynamic shading to an energy model to get a better sense of the overall energy use for our reference office. Thanks a lot, and I look forward to the next tutorial.